hope everyone can hear me because I don't really want to scream because I will lose my voice soon. So here, today I will talk about this crystallization of carbonate minerals in organic matrices. So I will start by giving you some example of these organic matrices in organism, and then I will also give you some. Okay. Doesn't work. Does it work?
Yeah, sure.
Okay. So then I have to stay here. So here, so I will start by giving you some example about the organic matrices from the organism, and then I will show you a bit about the biomimetic we are working on. And this research is a strong collaboration between a group in Madrid and also a center of electron microscopy in Ulm, also in Germany. So then here I will start with these microplatelets. So here from the gastropod aragonates, you can see that this is the aragonate platelet growing, and also here the preformed interlamellar matrix that becomes minerals. And the most important thing here is that you can see from here that there is a bridge, mineral bridge between the aragonate platelet and also the presence of this organic matrix. And here I will give you the real example from the animal. It's Mytilus edulis. So you have these aragonate platelets, and you can see that there is organic matrices surrounding these aragonate platelets. And then when you add or you decalcify a little bit the aragonate platelet, you can see the organic matrices on the aragonates. Another example is from this fibrous calcite here. So here I have two different colorful stars. The first one is the blue one. So if you see carefully in this blue one, this organic matrices is the organic matrix that you can see surrounding the fibrous calcite. And the other organic matrix is this red star over here. So this organic matrix is present on the fibrous calcite. So here from this example, you can see two different organic matrices. So what we are doing in Munich is that we are trying to crystallize or to mineralize this calcium carbonate using the hydrogels, because we believe that this hydrogel has similar or resemblance to these biomineralization conditions. So then we're hydrogels because we have so many different kinds of hydrogels. We can start from the agarose, gelatin, or silica hydrogel. You can also have polyacrylamide hydrogels. Then you can also modify the surface of the hydrogels. So here that's where I use these three different hydrogels to start with: the gelatin, agarose, and silica hydrogels. And each hydrogel has a different diffusivity, also functional groups I explained to you before, and then also in the aqueous phase compositions. And to start these experiments, we have a so-called double diffusion system. This is not a new system. I mean, it has been used by so many people since 1996 or even older than that. So here in this system, you have these hydrogels in the middle. And then you have those two sources here. This is for the calcium, and this is for the sodium. Then you expect that the crystal of this calcium carbonate crystal will grow in these hydrogels. And in our system, we also put magnesium inside of this hydrogel system. So then we'll also see the effect of this magnesium on this calcium carbonate growing crystal. So I will start by showing you the aggregate that we obtain from this system. Here we are. So here, this is really clear that you can see from just this one slide, there are a lot of variations in this morphology. So we can start from this silica. So here you have a little bit Hooper crystals, and then if you see in this surface morphology, you can see this bit of roughness of this aggregate. But in the contrary, if you use these hydrogels, these agarose hydrogels, you see this elongated along the C-axis, and also you have this kind of aggregates. The most interesting part is that you have this porous surface morphology. But then if you have this gelatin, this is totally different morphology. I will show to you that this is kind of spherulites. I will show you the mesenteric orientations of this gelatin this crystal. And also the most interesting part, you see this surface morphology of this aggregate. It has a sub-block with less than 5 micrometer. What we can draw a conclusion from this just only one slide, that by changing this hydrogels, you change the morphology. And why is it so? Then we keep asking, why? Because then, this agarose, everyone should know that this agarose is a polysaccharide hydrogels. It has a polysaccharide groups in this hydrogels. And the gelatin, it's a polypeptide. That's why it's promote this kind of morphology. And then the other interesting part is about the presence of magnesium inside of the hydrogels. So here I go to the next slide. So here it's totally different morphology. Then I will start by explaining about the silica hydrogels. So here we did some surface EDX analysis to see the incorporation of magnesium on the surface of this aggregate. So here you have the content of magnesium incorporation here, and also this one has 0.038. So this morphology has a bit higher incorporation of the magnesium. But then if we go to this agarose hydrogels, the morphology changes. And also the incorporations of magnesiums also changes. Here you have this higher incorporation in this agarose hydrogel is 0.042, and you have a bit spherulite morphology. But then if you have this gelatin, or even this gelatin, this aggregate grown is in the gelatin hydrogel, it has magnesium incorporation of 17.9, which is close to 18. This is interesting because, like I explained it to you, it has polypeptide. It promotes the incorporation of this magnesium. And then we have also this surface morphology of those aggregates. Here with the silica, we have this porous surface morphology also here. But with agarose and the gelatins, we have the morphology of this blocky surface. And by increasing this magnesium incorporations, you have smaller blocky surface here. It's less than 1 micrometer. Okay, so I told you before that we knew that some of them were spherulites because we did some internal misorientations investigations. And the method that we used was electron backscatter diffractions. Okay, maybe it can take 30 minutes or even more just to explain how the system works because it's really sophisticated method. So I just give you a short introduction about the result we can obtain from this EBSD. So I will start with this crystallographic 3D. So this is we can obtain from the EBSD. And also on the other one, we have this stereographic projection. And from this stereographic projection, we have one C-axis and 3 A-axis. For example, in this example here, so you have the C-axis over here. You can imagine that this crystal is going toward these directions. And you have the 3 A-axis here, which means the 3 axis is, I don't know, this is the C. So you have the 3 A-axis here. So then you can imagine that the crystal is going into direction just for the C-axis. And the other result we can get from the electron backscatter diffraction in this color code map. So what's important from this EBSD is that you have one color which represents one crystallographic orientations. So here you have, I would call it aggregates. So in this aggregate, you have several colors. And this one color represents one subunit in this aggregate. And each subunit has one crystallographic orientations. So you can say that this yellow has crystallographic orientation along this direction. And if you see the red, it has another directions. So this aggregate has several subunits with different crystallographic orientations. Another example is here. You have the color gradient from a bit dark blue into light blue, which means the tilting between each subunit is not so big. For example, this light blue is over here and the dark blue is a bit over here. I can also show you about how to calculate the different tilting between each other, because I will show it to you also. So for this talk today, I will just show you mainly about this color code map result, and also a bit about this stereographic projection, and also this 3D crystallographic. So here we are. So I start with this aggregate going from the magnesium-free silica hydrogel. This is a bit funny because I told you that one color represents one crystallographic orientations, but then it has one color. But I will not say that this is one crystallographic orientations, because if you see here, this is the stereographic projection, the pole figure. You can see the gradients of this color starting from this bright purple or a bit blue to the dark blue purples, which mean that this is not the single crystal, because you have a different orientation tilting bit to each other. So it's not fully one crystallographic orientations. And also, if I draw this line from A to B, you can see the distance. This is, for example, 600, which doesn't make sense for me. And this one is, so you have this misorientation. So the misorientation is really small. It's 1 degree. So the tilting between each other is only 1 degree. But still, it's not a single crystal. If you talk with people from the crystal group, they will say single crystal there's no tilting. So here, so this is with magnesium-free silica. And then I will give you another surprise here. So this is with magnesium-bearing silica hydrogels. And just keep in mind that we really use high content of magnesium in the hydrogels. It's 0.1 molar. So it's a bit complicated here. So this is the crystallographic 3D here. And I would say it's half spherulite or partially spherulites. Why is it so? Because if you pay attention here in the middle, and you have the spherulites, at this, in the middle or the core of this aggregate, it has the C-axis pointing toward us. And then it is spherulites because the C-axis here is going toward the middle. So this is, I would say this is half spherulites. And also here, I will show you the fully spherulite later. The fully spherulite will give you C-axis in the middle and the A-axis around this core here. I will show it later to you. So this part of this aggregate has a spherulite, partially spherulite subunit. And the most interesting part of this aggregate here is that if you draw a line from A to B, so then I go to here, this is the line from A to B, you have this tilting between each subunit in this subunit is around 10 degrees. So if you pay attention here, it has color, it says red, and it's the gradient color changed to the bit orange, and then bright orange, and then this is yellow. And for this each subunit in this subunit has a tilting degree of around 10 degrees here. And then you go here and also here. I put an arrow here because it shows you that it's this part here of this subunity, it's not a single crystal. Because if you pay attention here, it's not a line, which means if it's not a line, there's a tilting. So then I will say that the subunit in this subunit is a mesocrystalline. So this is the calcite grown from this silica hydrogels. And then it's getting more interesting because then we use the agarose, which is the polysaccharide hydrogels. Okay, this is clear here. You have several subunits. You have this color here and also another here and here and here. But the most interesting part is that if I take the pole figure only for this subunit number 4, then I have this 1 dot. In it, it's not a 1 dot because if you see it has 61,000 data points. But these 61,000 data points taking into each other, which also means it's really close to a single crystal. And also if I draw a line along A to B, you see the misorientation is 0.5. The machines can detect the misorientation until 0.2. This is really powerful. This EBAC method is really powerful. And then, so then this aggregate has this subunit close to a single crystal. But then with magnesium, it changes everything. So that's what I call a spherolite. So here you start with the c-axis. So the c-axis is going toward us, but it has scale a bit bigger, which means that the c-axis is going in these directions, and the a-axis is rotating like this. You can also see it from here. So this is the spherolite grown from magnesium-bearing agarose with the agarose inside of the hydrogel 0.1 molar. And here, if I draw a line from A to B, so the misorientation is not so high, and it's not so big. But then if we go to the other part, the misorientation is getting higher. The degree of this misorientation is getting higher, which is normal for the spherolites, because you have smaller grain in the middle and bigger grain outside. So then this is from the agarose, and we have the last hydrogel is from the calcite. So this is from magnesium-free gelatin. This is interesting because with magnesium-free agarose and magnesium-bearing silica hydrogel, it doesn't give you really complicated morphology. But when you use gelatin, because it has the polypeptide and it promotes the incorporation of magnesium into the crystal, into the aggregate, then it totally, this is with magnesium bearing. So yeah, the gelatin itself already gives you some effects on the misorientations. And it appears there's a partial spherolite again. And also if you draw a line from A to B, it gives you misorientations. And also from C and D, it jumps from this part because it has a big subblock here, over here from the C. And then it's static again, and then it jumps again because of this big subblock. And with this one, it has a fully spherolite with the c-axis going toward us outside. And the a-axis is also rotating. And this misorientation gives you this kind of degrees, starting from 20, and then it drops again. We are still working on it because it will be in the newest paper that I hope we can publish it next week. So it seems that I have only 2 minutes. In it, I have more than 5 slides. So I will just start a bit faster. So this is the etching experiments to show you the incorporation of the hydrogels. The incorporation of the hydrogels. And this is the silica particle that you see. It's incorporated into the calcite aggregate, and also here you can see the incorporation of the silica hydrogel in the calcite. So it doesn't. That's why it doesn't really give a lot of effects, because then it doesn't really change the orientation. But here, okay, then you have this incorporation of the hydrogels here. It has these membranes, the presence of the membranes. This is without magnesium, and then with magnesium there's no membrane anymore. Only this fiber, and this one is only this fiber. And the last one is this gelatin. You really have this thick membrane, the incorporation of thick hydrogel into the calcite aggregate. But when there's magnesium, the thickness is getting less and less. So this is this membrane, and here this membrane is getting less thicker. Okay, so this is the cryo-SEM. Just to show you how the silica hydrogel looks like without any crystal. And this is how the agarose looks like. And this is how the gelatin looks like. So those two are the fibrous hydrogels, and this one is just silica particle with size of 20 nanometer. And then we also did this decalcification of the aggregates to show you how the hydrogel looks like after the crystallization of calcium carbonate. So here it doesn't change. It still looks the same mostly. And here, this is after the decalcification, using the presence of these fibers, still the same. And the crystal, we believe that it's going inside of these pores. And this is also with the gelatin, the crystal, we believe that it's also going here. So then, we show you all these hydrogels, and now I will show you about the example from the organism. So here, this is the presence of the membrane from the gastropods. And this one is from the calcite fiber that you can see these membranes also. And this is the closer look of those membranes. And also here you have the voids in the membranes, which we believe that it gives information of the crystal to the next crystal about how it grows. So there's a connections. And this is the organic matrices from bivalves. And this is also here you can see the membranes. And then the next one is these fibers that you can see from the bivalve aragonates, these necrotablets. And this is from the gastropod aragonates. And this is from the calcite part of the gastropod. So, and the coralline algae, red algae. And the conclusion. So then silica hydrogel has little effects, especially without magnesium in the growth medium. And gelatin hydrogel has the most pronounced effect with and without magnesium. And gelatin incorporates more magnesium, followed by agarose and silica hydrogels. Gelatin and agarose hydrogel fabric show some resemblance to organic matrices observed in modern carbonate biological skeleton. And up to now, we do not really reproduce all the thick membranes we saw from the organic organism. However, we find similarities between agarose and gelatin fiber accumulations in biomimetic gel mineral composite and fiber assemblages in natural carbonate skeleton. So this is from the agarose, from the hydrogel, and this is from the organism. So you can see whether it looks the same or not, and then you can just think about it. And then, can hydrogel be used to mimic organic matrices in carbonate biological hard tissue? Only to some extent. Thank you, and sorry for long talks.